Imagine staring into the night sky, watching the familiar dance of stars, only to witness something that shouldn't exist. A flicker of light where there should be darkness. A celestial object moving in ways physics can't explain. This isn't science fiction. It's the reality astronomers face every time they uncover one of the universe's best-kept secrets, cosmic anomalies so baffling they rewrite the rules of what we think we know. From stars that vanish without a trace to galaxies spinning backward against the laws of gravity, the cosmos is filled with mysteries that leave even the brightest minds in science utterly stumped. This is a journey into the unexplainable, a deep dive into 25 cosmic anomalies that defy logic, challenge our understanding, and ignite our curiosity like nothing else. These aren't just oddities, they're cosmic puzzles, pieces of a universe that refuses to be tamed by equations or telescopes. Some are whispers in the dark, signals with no known source. Others are colossal, like the Great Attractor, a gravitational mystery pulling entire galaxies toward it with unseen force. What ties them together? They all stand as humbling reminders that space, for all its vastness, is still a realm of endless surprises. So why do these mysteries matter? Because every anomaly is a question waiting to be answered, a key to unlocking deeper truths about existence itself. They force us to rethink the boundaries of reality, to challenge the limits of human knowledge, and as we explore them together, you'll discover just how strange, how wondrous, and how utterly unpredictable the universe truly is. This isn't just a list, it's an invitation to step into the unknown, to witness the cosmic phenomena that keep scientists awake at night, ready to unravel the enigmas hidden among the stars. Let's begin. On the night of August 15, 1977, a radio telescope in Ohio picked up something extraordinary, a burst of sound so powerful and so peculiar that the astronomer who discovered it scribbled, "Wow," in red ink right on the data printout. That single word gave the signal its name, but the mystery behind it has endured for decades. For 72 seconds, this radio emission blasted through the cosmos, coming from a region near the Sagittarius constellation with no known stars or planets. Then, just as suddenly as it appeared, it vanished, never heard again. What made the wow signal so strange wasn't just its intensity, but its frequency. It hit exactly at 1420 megahertz, a range scientists had long considered a prime candidate for interstellar communication because it's naturally quiet in space. No known cosmic phenomenon, no pulsar, no quasar, no stellar flare matches its peculiar signature. Some researchers argue it could have been a one-off event, like a comet reflecting sunlight in just the right way. But no comet was found along that precise path. Others suggest an artificial origin, a fleeting message from some distant intelligence. The problem, despite decades of listening, we've never caught another whisper like it. The wow signal stands alone, a cosmic flare in the dark, a question without an answer. It teases us with possibilities. Was it a natural oddity we don't yet understand? Or something far more profound? Either way, it's a reminder that even our most advanced tools can't decode all the universe's secrets, and that's what makes it so thrilling. Because somewhere out there, whether it's physics we haven't mastered or a voice we haven't recognized, the truth is still waiting to be found. Picture this, an entire universe where most of the matter is invisible. Not hidden behind dust or clouds, but completely undetectable by any telescope or instrument we've ever built. Yet its presence is undeniable, bending the very fabric of space and shaping the fate of galaxies. This is dark matter, the ghost in the cosmic machine, making up roughly 27% of everything in existence. And despite nearly a century of searching, we still don't know what it is. The story starts in the 1930s when astronomer Fritz Zwicky noticed something bizarre about the Coma cluster, a group of galaxies over 300 million light-years away. The galaxies were moving so fast that they should have torn apart unless there was something else holding them together, something invisible with enough gravity to keep them in check. Decades later, Vera Rubin's observations of spinning galaxies confirmed it. Stars on the outer edges moved just as quickly as those near the center, defying Newton's laws. The only explanation, an enormous halo of unseen matter, its gravitational pull keeping everything from flying apart. So why is dark matter so hard to find? Because it doesn't behave like ordinary matter. It doesn't emit, absorb, or reflect light, hence the name. It doesn't form stars, planets, or even dust. It barely interacts with anything at all, passing right through you at this very moment without a trace. Scientists have built detectors deep underground, shielded from cosmic rays, hoping to catch a rare collision between dark matter particles and atoms. Others scan the skies for distortions in starlight, subtle bends caused by dark matter's gravity. So far, nothing definitive. Theories abound. Maybe dark matter is made of WIMP, weakly interacting massive particles that only reveal themselves under extreme conditions. Or perhaps its actions, hypothetical particles so light they barely register. Some even suggest we're missing something fundamental, that gravity itself works differently on cosmic scales. Every experiment deepens the mystery. Take the Bullet Cluster, where two galaxies collided and their dark matter kept right on going, unaffected, while visible gas slammed together in a brilliant flash. Proof it's real, yet still beyond our grasp. Dark matter isn't just a footnote in astrophysics, it's the scaffolding of the universe itself. Without it, galaxies wouldn't form, and the cosmos as we know it wouldn't exist. But for all its influence, it remains a shadow, a cosmic riddle wrapped in gravitational clues. And until we crack it, we're left with this humbling truth. Most of the universe is made of something we can't even see. If dark matter is the invisible hand shaping the cosmos, then dark energy is the unseen force tearing it apart. Picture the universe not just expanding, but doing so at an ever-increasing rate, like a runaway train hurtling faster with each passing second. This bizarre phenomenon defies everything we thought we knew about gravity and cosmic evolution. And the most startling part, dark energy makes up a staggering 68% of the universe, dwarfing even dark matter in its dominance. Yet we have no idea what it actually is. The discovery reads like a scientific plot twist. In the late 1990s, two teams of astronomers were studying distant supernova exploding stars used as cosmic mile markers to measure how quickly the universe's expansion might be slowing down. The prevailing belief was that gravity, pulling everything inward, would eventually break that expansion, but their data revealed the opposite. These supernovae were fainter than expected, meaning they were farther away than calculations predicted. The universe wasn't just expanding, it was accelerating. The only explanation, some mysterious repulsive force counteracting gravity on the grandest scales. The name dark energy was coined, but the mystery only deepened. What makes dark energy so baffling is how it behaves. Unlike matter or radiation, its density doesn't dilute as the universe grows. Instead, it seems woven into the fabric of space itself, a property Einstein once called the cosmological constant, before dismissing it as his greatest blunder. Now it's back with a vengeance. Some theories suggest dark energy could be the energy of empty space, a quantum foam of particles flickering in and out of existence. Others propose a dynamic field nicknamed quintessence that changes over time, but every attempt to pin it down leads to more questions. Why does it dominate now, 8 billion years after the Big Bang? Could it grow stronger, eventually ripping apart galaxies, stars, even atoms in a theoretical Big Rip? The implications are staggering. Dark energy doesn't just accelerate expansion, it determines the ultimate fate of the cosmos. If it strengthens, the universe could end in cold, empty isolation. If it weakens, gravity might regain control, collapsing everything in a big crunch. And then there's the unsettling coincidence. The amount of dark energy we observe is fine-tuned to an absurd degree. Alter it by even 1 part in 100 million billion, and life as we know it wouldn't exist. Is this luck or a clue to something deeper? For now, dark energy remains the ultimate cosmic wild card, an invisible puppeteer controlling the universe's destiny. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map its influence with unprecedented precision. But until we crack this enigma, one truth lingers: the universe isn't just stranger than we imagined. It's stranger than we can imagine, and dark energy is the proof. Imagine the Milky Way along with thousands of other galaxies caught in an invisible current, all drifting toward a single point in space like leaves swept up in a cosmic river. This is the Great Attractor, a gravitational anomaly so powerful it bends the paths of galaxies across hundreds of millions of light years. But here's the catch: we can't see it. Lurking behind the Milky Way's own starlit disk, in a region astronomers call the zone of avoidance, this enigmatic force remains shrouded in mystery, its true nature just out of reach. The story begins in the 1970s when scientists mapping galaxy motions noticed something inexplicable. Our local galactic neighborhood, including the Milky Way, wasn't just drifting aimlessly, it was being pulled with alarming speed toward a specific patch of sky near the constellations Centaurus and Hydra. The culprit, a gravitational focal point with the mass of tens of thousands of Milky Ways, warping spacetime itself. But when researchers aimed their telescopes in that direction, they hit a wall, literally. The zone of avoidance, a thick band of dust, gas, and stars from our own galaxy's plane, blocks nearly all visible light from beyond. It's like trying to peer through a fogged-up window while standing in a spotlight. For decades, the Great Attractor was a cosmic ghost, felt but not seen. Then, in the 21st century, new tools changed the game. Infrared and radio telescopes capable of piercing the galactic fog revealed clusters of galaxies previously hidden, massive structures like the Norma cluster, dense with galaxies and hot gas. But here's the twist: even these colossal formations weren't enough to explain the full strength of the pull. The Great Attractor, it seemed, was just the tip of something far larger. Enter the Laniakea supercluster, a mind-bending web of galaxies spanning 500 million light-years, with the Great Attractor as its gravitational heart. Picture a vast cosmic watershed where galaxies flow like rivers into a single basin. Yet this still doesn't solve the riddle. Recent studies suggest an even grander force at play: the Shapley supercluster, a gargantuan assembly of matter over 600 million light-years away, pulling the Great Attractor itself. It's a cosmic tug-of-war on scales so vast they defy intuition. Why does this matter? Because the Great Attractor isn't just a curiosity, it's a roadmap to understanding the large-scale structure of the universe. Its hidden location forces us to innovate, using everything from X-ray surveys to gravitational lensing to map the unseen. And with each discovery, we're reminded the universe holds its secrets close, especially when they lie in the shadows of our own galactic backyard. So while the Great Attractor remains elusive, one thing is certain: it's pulling us toward more than just a point in space. It's dragging us deeper into the unknown. One moment there's silence, the next, an explosion of energy so fierce it outshines entire galaxies. Fast radio bursts, or FRB, are the universe's most enigmatic flashes, packing more power in a millisecond than the sun emits in 80 years. These cosmic firecrackers erupt without warning, vanishing before we can even turn our telescopes toward them. And the strangest part, we still don't know what's causing them. The first FRB was discovered in 2007, buried in old radio telescope data from Australia. Since then, we've detected hundreds more, each a blink and you'll miss it burst of radio waves from galaxies billions of light-years away. Some repeat at random intervals, while others flare once and disappear forever. Their unpredictability makes them maddeningly hard to study, like trying to solve a puzzle where the pieces keep vanishing. So where do these bursts come from? One leading suspect is magnetars, neutron stars with magnetic fields so strong they could wipe a credit card clean from halfway across the Milky Way. In 2020, astronomers caught a magnetar in our own galaxy emitting an FRB-like signal, the strongest evidence yet linking these exotic stars to the phenomenon. But not all FRBs fit this mold. Some are far too energetic, suggesting something even more extreme: colliding black holes, evaporating primordial stars, or cosmic strings, hypothetical defects in spacetime itself. Then there's the wild card. Could some FRBs be artificial? A few exhibit patterns so precise, they've sparked debate about whether we're seeing natural astrophysics or technology from an advanced civilization. One repeating burst, FRB 1212, pulses every 157 days like clockwork, a regularity that defies most natural explanations. Of course, extraterrestrial origins remain a fringe theory, but the very possibility underscores how little we understand. What makes FRBs so captivating isn't just their mystery, but what they reveal about the cosmos. As these signals traverse the universe, they interact with the sparse matter between galaxies, leaving fingerprints that let us map the universe's hidden structure. They're cosmic lighthouses illuminating the dark voids we can't otherwise see, and with every new detection we're reminded the universe is brimming with phenomena we've yet to imagine. Fast radio bursts aren't just anomalies, they're glimpses into the uncharted physics of the extreme, and the next one could rewrite the rules entirely. In the vast sea of stars, one flickering pinprick of light stands out as a cosmic riddle unlike any other. KIC 8462852, better known as Tabby's star, behaves in ways no other star should. Nestled in the constellation Cygnus, this seemingly ordinary star has baffled astronomers with its erratic dimming, sometimes dropping in brightness by up to 22% in ways that defy all known stellar behavior. The bizarre fluctuations sparked wild theories, from swarms of comets to something even more extraordinary, alien megastructures. The mystery began in 2015, when citizen scientists combing through data from NASA's Kepler Space Telescope flagged the star's peculiar light patterns. Unlike planets which cause predictable, periodic dips as they transit, Tabby's star dimmed irregularly, sometimes gradually, sometimes sharply, with no discernible rhythm. The deepest dips lasted for days, suggesting objects far larger than planets were blocking its light. When natural explanations fell short, speculation erupted. Could this be evidence of a Dyson swarm, a hypothetical alien megastructure designed to harvest a star's energy? The idea wasn't entirely fringe. Astrophysicist Freeman Dyson had once theorized that advanced civilizations might build such constructs. But science thrives on skepticism, and alternative theories soon emerged. Perhaps the star was surrounded by colossal dust clouds, remnants of a shattered planet or a chaotic asteroid belt. Observations in 2017 revealed the dimming was wavelength-dependent, more pronounced in blue light than red, a telltale sign of fine dust scattering light, not solid megastructures. Then there's the star's long-term dimming. Over the past century, archival data showed Tabby's star has faded by nearly 14%, an unprecedented trend with no clear explanation. Some propose a recent catastrophic collision in its system, littering its orbit with debris. Others point to internal stellar dynamics, like magnetic activity or slow pulsations, though no known star exhibits such extreme behavior. What makes Tabby's star so captivating isn't just the unanswered questions, it's the way it challenges our assumptions. Here's a cosmic puzzle where even the most outlandish ideas force us to rethink the boundaries of possibility. Projects like the Breakthrough Listen initiative have trained radio telescopes on the star, hunting for artificial signals amid the noise, so far silence. Yet the absence of answers is its own kind of revelation. Tabby's star reminds us that the universe is stranger than our textbooks suggest, and sometimes the most thrilling discoveries begin with a single, inexplicable flicker in the dark. Whether dust or something beyond our imagination is to blame, one thing's certain: this star isn't done keeping its secrets. The universe is unimaginably vast, with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of which host planets in habitable zones. Given the sheer numbers, the math suggests we shouldn't be alone. So where is everybody? This is the Fermi Paradox, a haunting contradiction that's puzzled scientists since physicist Enrico Fermi first posed the question in the 1950s. If life is likely to arise given the right conditions, and the cosmos has had over 13 billion years to produce it, why does the universe feel so eerily silent? One explanation is the Great Filter, a hypothetical barrier so extreme that it prevents life from advancing to interstellar scales. Think of it as a cosmic sieve, catching civilizations before they can spread across the stars. The chilling question is where this filter lies. Is it behind us, meaning we've already beaten astronomical odds to evolve at all? Earth's history hints at this possibility. Life appeared early, but intelligence took billions of years. Maybe microbial life is common, but multicellular complexity is vanishingly rare. Or perhaps the filter is ahead of us, lurking in our future. Climate collapse, nuclear war, or unchecked artificial intelligence could be the events that snuff out civilizations before they ever leave their home system. Then there's the possibility that intelligent life is simply too scattered. Space is mind-bendingly vast, and the distances between stars are colossal. Even at light speed, a signal from the closest star system would take over 4 years to reach us. If civilizations emerge but remain isolated by time and space, they might blink in and out of existence without ever crossing paths. Some researchers suggest that advanced societies might abandon radio transmissions, relying on technologies we can't yet detect, like neutrino communication or quantum entanglement. We could be listening for the wrong things, like searching for smoke signals in the age of the internet. Another unsettling idea is the zoo hypothesis, that other civilizations are aware of us but choose not to interfere, observing humanity the way we might study uncontacted tribes in the Amazon. Or worse, Earth might lie in a cosmic quiet zone, a region deliberately avoided due to some unseen danger. There's also the rare Earth argument, which posits that while simple life could be common, the conditions needed for technological intelligence, a stable star, a large moon to stabilize climate, plate tectonics to recycle minerals, are astronomically improbable. The Fermi Paradox isn't just about aliens, it's a mirror reflecting our own fragility and uniqueness. Every possible solution forces us to confront uncomfortable truths. Either we're precariously alone or we're doomed to never connect with others. Projects like SETI continue scanning the skies, while missions to Mars and Europa search for microbial fossils or extremophiles. Until we find proof, the paradox remains a humbling reminder. In a universe teeming with possibilities, silence might be the most profound mystery of all. Imagine peeling back the layers of the universe to reveal its earliest light, a faint glow from the dawn of time itself. This is the cosmic microwave background, or CMB, the afterglow of the Big Bang, imprinted on the sky like a fossil from 13.8 billion years ago. For decades, it's been our most reliable map of the infant universe, confirming predictions about its structure, expansion, and composition. But hidden in this seemingly uniform sea of microwaves lies something unsettling, a pattern so peculiar, scientists half-jokingly dubbed it the axis of evil. This isn't just a minor glitch, it's a series of anomalies in the CMB that, if real, could upend our understanding of the cosmos. The controversy starts with a simple expectation. The universe should be isotropic, meaning it looks the same in all directions. The CMB, as a snapshot of the universe's infancy, should reflect this: a nearly even distribution of hot and cold spots with no preferred orientation. But when NASA Wilkinson Microwave Anisotropy Probe and later the Planck satellite mapped the CMB with unprecedented precision, they found something unexpected. The fluctuations weren't entirely random. Instead, they seemed to align along a particular axis, as if the universe had a hidden, preferred direction. Even stranger, this axis loosely lines up with the plane of our solar system and the orientation of galaxies nearby, a coincidence so statistically improbable it defies explanation. Skeptics argue it could be an artifact of measurement errors or foreground interference from our own galaxy, but the anomalies persist even after accounting for these factors. One glaring example is the cold spot, an unusually large region in the CMB that's significantly cooler than the surrounding areas. Some theorize it might be a cosmic defect, a relic from exotic physics in the early universe. Others suggest it could be evidence of a collision with another universe in the multiverse scenario. Then there's the quadrupole and octupole moments, large-scale patterns in the CMB that appear suspiciously aligned, as if the universe has a subtle tilt we can't explain. The implications are profound. If the axis of evil is real, it challenges the cosmological principle, a cornerstone of modern physics stating that the universe is homogeneous and isotropic on large scales. Some researchers propose radical alternatives, like a universe that's fundamentally anisotropic, shaped by an early phase of rapid expansion that left behind directional imprints. Others entertain the idea of pre-Big Bang physics, where conditions before the birth of our universe set these patterns in motion. There's even the unsettling possibility that we're seeing the fingerprints of a far larger structure beyond our observable horizon, a cosmic landscape we can't yet perceive. What makes the axis of evil so captivating isn't just the scientific debate, it's the humility it forces upon us. Here we are, armed with the best telescopes and theories, staring at the oldest light in existence, and it's whispering that we might be missing something fundamental. Whether it's a statistical fluke or a clue to deeper laws, one thing is clear: the universe loves to surprise us, and until we crack this enigma, the axis of evil stands as a haunting reminder that even our most cherished models of reality are provisional, waiting for the next anomaly to rewrite them. In October 2017, astronomers spotted an object streaking through our solar system unlike anything they'd ever seen. Moving at nearly 200,000 miles per hour, it didn't orbit the sun it sliced through on a hyperbolic trajectory, a path so extreme it could only mean one thing. This visitor came from another star, named Oumuamua, Hawaiian for scout or messenger from afar. It became the first confirmed interstellar object ever detected. But what should have been a monumental discovery quickly turned into one of modern astronomy's most heated debates, because Oumuamua didn't behave like any ordinary comet or asteroid. The first red flag was its shape. Based on brightness variations as it tumbled, scientists concluded Oumuamua was highly elongated, roughly 10 times longer than it was wide, resembling a cosmic cigar or pancake. Natural objects this stretched are virtually unheard of. Most asteroids and comets are lumpy or spherical. Then there was its motion. As it raced away from the sun, Oumuamua accelerated slightly, as if pushed by an unseen force. Comets do this when their ices vaporize, creating a visible tail. But Oumuamua showed no gas, no dust, no coma, just bare, silent rock, unless, of course, it wasn't a rock at all. Harvard astrophysicist Avi Loeb stirred controversy by proposing an extraordinary explanation. Oumuamua could be artificial, perhaps a light sail, a thin, reflective structure pushed by starlight designed for interstellar travel. The idea wasn't entirely baseless. Its acceleration matched predictions for a lightweight object propelled by solar radiation pressure, and its unusual brightness suggested a reflective surface, possibly metallic. But critics fired back. Maybe Oumuamua was a rare type of dark comet, its outgassing too faint to detect, or a shard of a Pluto-like planet, rich in nitrogen ice that sublimated invisibly. Some even modeled it as a cosmic dust bunny, a fractal aggregate of interstellar material. The truth is, we may never know. By the time Oumuamua was spotted, it was already leaving, too distant for detailed follow-up. Future telescopes like the Vera Rubin Observatory aim to catch such visitors earlier. But what lingers isn't just scientific frustration, it's the tantalizing possibilities. Oumuamua showed us that interstellar objects are real, likely numerous, and capable of defying expectations. Whether it was a peculiar iceberg, a fragment of a shattered world, or something even more exotic, one thing is certain: the universe has more scouts waiting in the dark. And next time we'll be ready. High above Earth, in the silent expanse of space, something unusual has reportedly been circling our planet for thousands of years, long before humans ever launched a satellite. Meet the Black Knight, a shadowy object shrouded in conspiracy, said by some to be an ancient extraterrestrial probe watching over humanity. The stories range from eerie radio signals picked up by Nikola Tesla in the 1800s to grainy photographs allegedly snapped by NASA astronauts. But strip away the myth, and what remains is one of space's most persistent enigmas, a perfect storm of misunderstood science and cosmic folklore. The legend begins in the 1950s when newspapers reported that the U.S. and Soviet Union had detected an unknown object in polar orbit, an impossible feat at the time, since neither nation had yet launched a satellite capable of such a trajectory. Reports claimed it was 10,000 years old, broadcasting strange signals. Then, in 1960, Time magazine mentioned a mysterious, dark satellite orbiting Earth, further fueling speculation. By the 90s, internet forums buzzed with claims that the Black Knight appeared in NASA STS-88 mission photos, a blurry, jagged shape stark against the curvature of Earth. Reality, however, is far less cinematic. What conspiracists call the Black Knight is likely a patchwork of unrelated events and objects. The original detections were probably fragments of discovered space debris or even discarded thermal blankets from spacecraft, like the one photographed during STS-88. As for Tesla's intercepted signals, they almost certainly came from natural pulsars, celestial objects that emit regular radio bursts unknown to science in Tesla's day. But why does the myth endure? Because it taps into something deeper: our fascination with the idea that we're not alone, and that evidence of other civilizations might be hiding in plain sight. The Black Knight isn't just debris or static, it's a Rorschach test for our cosmic curiosity. Every generation reinvents it, layering new evidence onto old mysteries. Scientists may dismiss it, but as long as there are uncharted echoes in the void, the legend of the Black Knight will keep orbiting right along with them, a phantom in the machinery of the sky. Stretching across 330 million light-years of space, the Boötes Void is a cosmic desert so vast and empty it defies comprehension. Picture a sphere large enough to swallow thousands of galaxies, yet containing almost none. Just a scattering of isolated stars and the occasional dim galaxy, adrift in an ocean of nothingness. This eerie expanse, discovered in the 1980s by astronomer Robert Kirshner and his team, isn't just a gap in the fabric of the universe. It's a gaping hole in our understanding of how the cosmos organizes itself. At first glance, the void seems to violate one of astronomy's fundamental principles. The universe should look roughly the same everywhere on large scales. The cosmic web, with its filaments of galaxies and clusters, should leave no room for vacuums this extreme. Yet the Boötes Void exists, a region where matter didn't just thin out but seemingly vanished. To grasp its scale, imagine our Milky Way placed inside it. The nearest major galaxy would be tens of millions of light-years away, leaving our night sky almost pitch black, devoid of neighboring galaxies' glow. How does something this empty form? One theory points to primordial conditions. In the early universe, tiny quantum fluctuations ballooned during inflation, creating dense regions that became galaxy clusters, and underdense ones that became voids. But the Boötes Void is too big for this model alone. Some suggest it's the result of multiple smaller voids merging, like soap bubbles combining into one giant cavity. Others propose a more radical idea, that it's evidence of an ancient collision with another universe, a scar from a multiversal event we can't yet comprehend. Then there's the mystery of the few galaxies that do linger in the void. These isolated survivors, like the spiral galaxy MCG plus 0534067, shouldn't exist in such a barren environment. Their presence hints at hidden reservoirs of dark matter or unknown processes that allowed them to form against all odds. Or perhaps they're interlopers, flung into the void by gravitational interactions billions of years ago. The Boötes Void isn't just a curiosity, it's a laboratory for testing the limits of cosmology. By studying its edges, astronomers hunt for clues about dark energy's role in accelerating the void's expansion. Its emptiness even bends light differently, offering a unique window into gravitational lensing. And as telescopes grow more powerful, the void's secrets may finally emerge from the dark. Until then, it stands as a haunting reminder. The universe isn't just clumps of matter connected by threads. It's also defined by the spaces in between, the vast, silent voids where the rules, it seems, are still being written. In the vast emptiness between planets, where gravity's grip is supposed to be predictable, two tiny spacecraft defied expectations and left scientists scratching their heads for decades. The Pioneer anomaly began as a quiet mystery in the 1980s when researchers noticed something odd about NASA Pioneer 10 and 11 probes. These deep space explorers, launched in the 1970s to study Jupiter and Saturn, were drifting ever so slightly off course, not by much, just a fraction of a millimeter per second slower than they should have been. But in the precise world of orbital mechanics, even the tiniest discrepancy can signal something profound. At first glance, the numbers didn't add up. The spacecraft were experiencing an unaccounted-for deceleration, as if an invisible hand were gently tugging them backward toward the sun. The deviation was faint but persistent, showing up in data spanning years. Was it a flaw in our understanding of gravity? A sign of undiscovered physics like dark matter's influence or subtle errors in Einstein's equations? Theorists raced to explain it, proposing ideas ranging from exotic dark energy effects to modifications of Newton's laws at cosmic scales. The anomaly became a rallying cry for those questioning whether we'd missed something fundamental about how the universe works. Then came the twist, one that highlights science's knack for humbling even its brightest minds. After years of painstaking analysis, a team of researchers cracked the case in 2012. The culprit wasn't some revolutionary force or hidden dimension. It was heat, not from an external source but from the spacecraft themselves. Pioneer's nuclear power sources generated warmth, and as that thermal radiation leaked into space, it carried momentum, pushing back on the probes like a soft but steady breeze against a sail. The effect was tiny, but over billions of miles it added up. The anomaly wasn't a cosmic mystery after all. It was engineering, yet the Pioneer anomaly's legacy endures not as a failure of science but as a testament to its strength. Here was a puzzle so subtle it took 30 years to solve, a reminder that even our most precise instruments operate in a universe richer than our theories can predict. It's a lesson in curiosity. Sometimes the smallest deviations lead to the biggest insights, and while this mystery had a mundane explanation, the next one might not. After all, the universe loves to surprise us often in ways we least expect. Amid the delicate tapestry of the cosmic microwave background, where subtle temperature variations tell the story of the universe's infancy, one feature stands out like a cosmic bruise: the CMB Cold Spot. This mysterious patch, spanning nearly 1 billion light-years, is significantly cooler than its surroundings, as if something had siphoned energy from it long ago. At first glance, it might seem like a statistical fluke, but the odds of such a cold region appearing randomly are roughly 1 in 50, just unlikely enough to set off alarm bells among cosmologists. One leading explanation points to a supervoid, an enormous, mostly empty region of space where matter is sparse. The theory goes like this: as light from the CMB passes through such a void, it loses energy climbing out of the gravitational well, a phenomenon known as the integrated Sachs-Wolf effect. The problem: the cold spot's sheer size and temperature drop don't quite match any known voids in the nearby universe. Surveys have found a potential candidate, the Eridanus Supervoid, but it's not large or empty enough to account for the anomaly. It's like finding a footprint but realizing the shoe that made it doesn't exist. Then there's the more radical idea that the cold spot is a cosmic collision, a scar from an encounter with another universe. In the multiverse scenario, where our universe is one bubble among countless others, such collisions could leave imprints in the CMB. The cold spot's unusual polarization patterns and sharp edges add fuel to this theory, resembling what physicists predict a bruise from a neighboring universe might look like. But proving it is another matter. Without direct evidence of a parallel cosmos, the idea lingers at the edge of speculative science, tantalizing but unconfirmed. What makes the cold spot so fascinating isn't just its existence. It's the way it forces cosmologists to question their assumptions. If it's not a void or a multiverse artifact, then what? Could it be evidence of exotic physics, like a defect in spacetime from the universe's earliest moments, or a rare knot in the cosmic web, where dark energy's repulsive force created an unexpected cold pocket? Each possibility challenges our understanding of how the universe formed and evolved, turning this one anomaly into a battleground of competing theories. For now, the cold spot remains an open case, a cosmic detective story with no clear culprit. Upcoming telescopes like the Simons Observatory and CMB-S4 aim to study it with unprecedented precision, hunting for clues in its subtle light patterns. Whether it's a void, a multiverse relic, or something entirely unknown, one thing's certain: this enigmatic chill in the fabric of space isn't just a curiosity. It's a whisper from the universe, reminding us that even our best maps of reality might still be missing whole chapters of the story. We can map stars, galaxies, even dark matter's gravitational fingerprints, so how is it possible that half the universe's ordinary matter has gone missing? This is the missing baryon problem, one of cosmology's most perplexing accounting errors. Baryons, the particles that make up everything we can see, from planets to people, should be everywhere, woven into the cosmic web since the Big Bang. Yet when scientists tallied them up, nearly 50% were unaccounted for. The numbers didn't lie. Based on the universe's earliest light, the cosmic microwave background, there should be far more protons and neutrons out there than telescopes could find. For decades, this discrepancy haunted astronomers, suggesting either a gap in our observations or a flaw in our understanding of the cosmos itself. The breakthrough came not from peering deeper into the void, but from rethinking where to look. Conventional telescopes had scoured the skies for stars, gas, and dust, the obvious suspects, but the missing baryons weren't hiding in plain sight. They were lurking in the faint, diffuse filaments of the cosmic web, the vast scaffolding of gas and dark matter that connects galaxies across the universe. These strands, thinner than a single thread stretched across a football field, are so hot they glow in X-rays rather than visible light. And in 2017, two independent teams finally detected them using ESA's XMM Newton and NASA Chandra X-ray observatories. The discovery hinged on a clever trick. Instead of hunting for the filaments directly, astronomers studied how they distorted light from distant quasars, the brilliant cores of active galaxies. The distortions revealed a haze of superheated gas, millions of degrees Celsius, threaded between galaxies like invisible highways, but the mystery didn't end there. Even with these hidden reservoirs, the baryon budget still doesn't quite balance. Some theorists argue the remaining missing matter could be tied up in even harder to detect forms, perhaps as ultra-diffuse clouds of warm gas, or locked inside rogue black holes drifting between galaxies. Others suggest it might exist in exotic phases like quark-gluon plasma, remnants from the universe's fiery first moments. Then there's the wild card. Could some baryons have decayed into unknown particles over billions of years, slipping through the cracks of our detectors? The possibility, though speculative, underscores how much we still don't know about matter's cosmic life cycle. What makes the missing baryon problem so pivotal isn't just the hunt for hidden atoms, it's what it reveals about the universe's structure. These elusive particles aren't just passive bystanders, they're the raw material for everything we see. Their distribution shapes how galaxies form, how light travels, even how the cosmic web evolves. And as telescopes like the upcoming Athena X-ray Observatory peer deeper into these invisible threads, they're not just solving an old puzzle. They're rewriting the map of the universe, one faint, glowing filament at a time. The lesson, sometimes, what's missing teaches us far more than what's already been found. Most nebulae in the cosmos swirl and twist like celestial ink dropped into water, their shapes sculpted by chaos and chance, but not the red rectangle. Floating 2,300 light-years away in the constellation Monoceros, this cosmic oddity defies nature's preference for curves, displaying near-perfect geometric symmetry that looks more like a laser-etched hologram than a stellar phenomenon. Its stark, angular structure, two intersecting cones of glowing gas forming an X-shape with ladder-like rungs of dust, is so precise early astronomers mistook it for a lens flare or imaging artifact. But the red rectangle is very real, and its existence challenges everything we know about how dying stars sculpt their final acts. The mystery begins with its central star, HD 44179, a sun-like giant in its death throes. As it sheds layers of gas, we'd expect a typical planetary nebula, a glowing, irregular bubble like the Ring Nebula. Instead, the expelled material has organized itself into this bizarre, quasi-crystalline structure. One leading theory points to an unseen companion star, its gravity shaping the outflow into twin jets that collide, creating shockwaves that mold the gas into geometric planes. But even this can't fully explain the nested rungs of dust, which resemble steps on a cosmic staircase. Some researchers speculate these could be zones where carbon-rich molecules condense like snowflakes in midair, stacking in perfect intervals. Then there's the color. The red rectangle owes its eerie crimson glow to an unusual chemical cocktail, specifically polycyclic aromatic hydrocarbons (PAH), complex organic molecules more commonly found in soot or engine exhaust. These carbon-based compounds fluoresce under ultraviolet light from the dying star, painting the nebula in hues so vivid they've been described as blood soaked in neon. But PAHs this abundant shouldn't exist here. They typically form in the violent environments of young stars, not the quiet demise of an old one. Their presence hints at undiscovered chemistry, perhaps catalyzed by the nebula's unique geometry or hidden magnetic fields. What makes the red rectangle truly extraordinary isn't just its appearance, it's the questions it forces us to confront. Are we seeing a rare phase of stellar evolution, one where physics and geometry align just so? Or is this a glimpse of how binary stars can choreograph matter into shapes nature rarely produces? Future observations with telescopes like the James Webb Space Telescope aim to dissect its dust lanes molecule by molecule. But for now, the red rectangle stands as a cosmic paradox, a place where chaos gives way to order, where chemistry defies expectations, and where the universe once again proves it has a flair for the dramatic. At first glance, the universe appears random, a scatter of galaxies adrift in the dark, but zoom out far enough and patterns emerge, some so immense they threaten to rewrite the rules of cosmology. Enter the Hercules Corona Borealis Great Wall, a galactic superstructure so vast, its existence pushes the limits of what we thought possible. Stretching an astonishing 10 billion light-years across, this filament of galaxies and galaxy clusters is the largest known structure in the observable universe. To put that in perspective, it spans roughly 1/9 of the entire cosmos, a scale so incomprehensible it makes our local supercluster look like a speck of dust in comparison. Discovered in 2013 by a team analyzing gamma-ray bursts, the violent death throes of massive stars, this colossal wall defies the cosmological principle, the foundational idea that, on large scales, the universe should appear relatively uniform in all directions. Instead, the Great Wall suggests a cosmos with shocking irregularities, where matter clumps together in ways our models struggle to explain. Imagine tossing confetti into the air, only to watch it arrange itself into a single, perfect line stretching across the sky. That's the level of statistical impossibility we're dealing with, yet not all astronomers are convinced. Skeptics argue the Great Wall might be a trick of perspective, multiple smaller structures lining up by chance along our line of sight, like distant mountain ranges appearing connected from a single vantage point. Others question whether gamma-ray bursts, used as tracers to map the wall, are reliable markers for galaxy density. After all, these explosions tend to occur in star-forming regions, which could skew the apparent distribution of matter. The debate cuts to the heart of how we understand cosmic evolution. If the Hercules Corona Borealis Great Wall is real, it implies unknown forces shaped the early universe, perhaps traces of primordial quantum fluctuations far stronger than predicted. Some theorists even speculated could be a remnant of cosmic strings, hypothetical defects in space-time left over from the Big Bang, or worse, that our standard model of cosmology, the very framework guiding modern astrophysics, might be missing a critical piece. For now, the Great Wall lingers at the edge of discovery and doubt. New surveys, like those from the Euclid Space Telescope, aim to settle the controversy by mapping galaxy distributions in 3 dimensions. Until then, this titanic structure stands as both a marvel and a warning, a reminder that the universe, for all our charts and equations, still holds enormities we're only beginning to glimpse. Whether illusion or reality, one thing is certain: the cosmos refuses to play by the rules we've written for it. In 2019, astronomers scanning the sky with Australia's ASCAP radio telescope stumbled upon something no one expected: ghostly rings of radio emission, so vast they could swallow entire galaxies. These odd radio circles, or ARC, appeared as perfect, faint halos in the radio spectrum, invisible to optical telescopes. None of the usual suspects, supernova remnants, planetary nebulae, or even galaxy collisions, could explain their sheer size or symmetry. Each ORC spans hundreds of thousands of light-years, dwarfing the Milky Way, and they float in the cosmic void with no visible source at their centers. The discovery sent shockwaves through astrophysics because these enigmatic structures don't just challenge our understanding of space, they defy it entirely. What makes ORCs so baffling isn't just their scale, but their isolation. Most cosmic phenomena leave traces across multiple wavelengths: X-rays, infrared, or visible light. But ORCs exist only in radio waves, like whispers in a frequency only the universe seems to hear. Early theories ranged from the dramatic intergalactic shockwaves from gargantuan black hole mergers to the exotic, like cosmic strings, hypothetical defects in spacetime predicted by string theory. Some even speculated they might be the aftermath of wormhole activity, their circular ripples echoing through the fabric of reality, but none of these ideas fully fit. Shockwaves would dissipate unevenly, and cosmic strings should produce sharper edges, not the smooth, diffuse rings we observe. Then came an even stranger clue. Some ORCs appear to encircle galaxies with actively feeding supermassive black holes. Could these invisible giants be powering the rings, their jets bending into perfect loops under unknown conditions? Simulations suggest that under extreme circumstances, black hole winds might expand in spherical bubbles, lighting up radio emissions at their edges. But the energy required would be staggering orders of magnitude beyond what any known black hole can produce. Others propose ORCs are relics of past cataclysms, like the fading echoes of a quasar's death scream reverberating across millions of years. The more we learn, the deeper the mystery grows. Recent observations reveal some ORCs contain galaxies rich in star formation, hinting at a possible connection to intense bursts of stellar birth. Yet their perfect circularity remains unexplained. Nature rarely creates such precise geometries without a guiding force. Are we seeing the fingerprints of dark matter, its invisible mass sculpting these rings? Or something entirely new, a phenomenon we've yet to imagine? For now, ORCs stand as cosmic graffiti, cryptic signatures spray painted across the void. With every new detection, only a handful have been found so far. They taunt us with their silence, no visible sources, no clear mechanisms, just hauntingly beautiful loops hanging in the dark. And that's what makes them thrilling, because in a universe where we've mapped galaxies down to their smallest details, the fact that something this enormous, this strange, could still appear out of nowhere. That's not just a puzzle, it's an invitation to look harder, to rethink, and to embrace the humbling truth that space still has secrets we've only begun to glimpse. Somewhere in the constellation Cancer, 40 light-years from Earth, a planet exists where the phrase, "diamonds are forever," takes on a whole new meaning. 55 Cancri isn't just a rocky world, it's a jewel of the cosmos. A super-Earth so rich in carbon that scientists believe much of its mass could be crystallized into diamond. Imagine a world where mountains aren't made of granite but of glittering gemstone, where the very ground beneath your feet, if you could stand on it, would scratch every known mineral on Earth. This isn't science fiction, it's a real, documented exoplanet, and its existence forces us to rethink what planets can be. Discovered in 2004, 55 Cancri orbits so close to its sun-like star that a year lasts just 18 hours. Surface temperatures soar above 2000 degrees Celsius, hot enough to melt steel, yet not quite enough to vaporize diamond. That's where things get fascinating. Most rocky planets, like Earth, form from silicon and oxygen-rich material, giving us familiar crusts of granite and basalt. But 55 Cancri seems to have formed in a carbon-heavy environment where oxygen was scarce. Under immense pressure and heat, that carbon likely compressed into diamond, creating a mantle that could be hundreds of kilometers thick. Picture an entire layer of Earth's interior replaced by a solid sheet of gemstone, except here it's not a decorative rarity. It's the planet's bedrock, but the diamond isn't even the strangest part. This world is tidally locked, meaning one side forever faces its star while the other drowns in eternal night. The day side might host rivers of molten silicon or carbon lava, while the night side, if any atmosphere exists, could harbor surreal diamond rains. Some models even suggest the planet could have graphite plains on its surface, shifting like sand dunes under extreme stellar winds. And then there's the density. 55 Cancri weighs about 8 times as much as Earth, but is only twice as wide, packing its mass into a space that defies typical planetary composition charts. What makes this world truly groundbreaking isn't just its extravagance, it's the proof that planets can form from entirely unexpected recipes. If carbon-rich environments like this exist, then the universe might be peppered with worlds made of materials we'd consider exotic. Imagine diamond-encrusted gas giants or graphite worlds where the skies rain ink. 55 Cancri is a reminder that nature's creativity outstrips our imagination, crafting realms where the rules of chemistry and geology rewrite themselves under alien stars. As we keep searching the cosmos, one thing's certain: there are more jewels out there waiting to be discovered, and each one could redefine what we think a planet is. Deep in the heart of our galaxy, something stirs a sleeping giant with the power to reshape life on Earth from 26,000 light-years away. Meet Sagittarius, a star, the supermassive black hole anchoring the Milky Way. While most black holes are content to devour nearby matter in silence, some scientists believe ours periodically awakens in violent outbursts, sending shockwaves of cosmic radiation rippling outward like a stone dropped in a pond. These aren't just any shockwaves. According to the controversial galactic superwave theory, they could be responsible for mass extinctions, climate shifts, and even ancient myths of celestial fire. The idea hinges on a startling premise. Every 12 to 15,000 years, Sagittarius, a star, may unleash cataclysmic bursts of gamma rays and cosmic rays energy tsunamis so powerful they could penetrate Earth's atmosphere, irradiate the surface, and trigger cascading disasters. Proponents point to eerie clues buried in ice cores and sediment layers. Samples from Greenland and Antarctica reveal spikes in radioactive isotopes like beryllium-10 and chlorine-36, dating back to periods coinciding with extinction events and abrupt climate changes. Then there's the Younger Dryas event, a sudden plunge into Ice Age conditions around 12,800 years ago, just as human civilizations were emerging. Geological strata from that time contain nanodiamonds and melted glass, telltale signs of extreme heat, possibly from a bombardment of high-energy particles. Skeptics, of course, demand harder proof. Galactic superwaves would require the black hole to behave unlike any we've observed, flaring with energies far beyond its usual activity. And timing the eruptions is nearly impossible without a reliable galactic clock. But here's where it gets intriguing. If these waves are real, they might leave fingerprints in human history. Ancient cultures worldwide describe apocalyptic fires from the sky, the Egyptian heavenly iron, the Vedic Agni, even Plato's tale of Atlantis consumed by celestial flames. Could these be garbled accounts of a superwave's aftermath? The implications are staggering. A modern superwave could fry satellites, collapse power grids, and bathe the planet in radiation for years. NASA's Fermi Gamma Ray Space Telescope now scans for such threats, but detecting one in time remains a gamble. Meanwhile, astronomers debate whether the theory is groundbreaking or galactic ghost stories. Either way, it forces us to confront a humbling truth. We're not just passengers on a planet. We're sailors on a cosmic ocean, subject to tides we're only beginning to sense. And sometimes the waves come from places we never thought to fear. Out beyond Neptune, where the sun is just a bright star in an endless black sky, our solar system doesn't taper off gently. It ends with a cosmic gut punch. This is the Kuiper Cliff, a boundary so abrupt it's like someone drew a line in the celestial sand. The Kuiper Belt, that ring of icy debris where Pluto calls home, should theoretically stretch much farther, with countless frozen worlds dwindling slowly into the void. But around 50 astronomical units from the Sun, about 7.5 billion kilometers out, the number of objects drops off a cliff. It's not a gradual fade. It's a hard stop, as if something swept the outer solar system clean, and that something might still be out there, one leading suspect, a hidden planet lurking in the dark. Not just any planet, a massive, undiscovered world, perhaps 5 to 10 times the size of Earth, its gravity shepherding the Kuiper Belt into this unnatural edge. Astronomers call it Planet 9, and while it's still hypothetical, the math is compelling. Strange orbits of distant objects like Sedna and Biden hint at an unseen gravitational influence, something big enough to tug them into odd, elongated paths. If Planet 9 exists, its distant, tilted orbit could explain the Kuiper Cliff, either by slingshotting objects inward or ejecting them entirely. Imagine a cosmic janitor silently rearranging the solar system's furniture over billions of years. But not everyone's convinced. Alternative theories argue the cliff might be a relic of the solar system's violent birth. During those chaotic early years, Neptune's migration could have scattered debris, leaving a sharp cutoff in its wake. Or perhaps it's a shadow of the Sun's ancient environment, a region where the protoplanetary disk thinned abruptly, starving outer planets of building material. There's even a wilder idea. The Kuiper Cliff might mark the edge of the Sun's original stellar nursery, a boundary where the gravitational pull of sibling stars in a long-vanished cluster stripped away leftover planetesimals. What makes this mystery so crucial isn't just the missing objects, it's what they could tell us about our cosmic neighborhood's past. The Kuiper Belt is a fossil record, preserving clues about how planets formed and moved. A hidden planet would rewrite solar system history, proving we've overlooked a major player. A dynamical relic, on the other hand, would reveal how violent and unpredictable planetary infancy really was. Every new survey of the outer solar system, like the Vera Rubin Observatory's upcoming decade-long scan, brings us closer to answers. Until then, the Kuiper Cliff stands as a silent sentinel, guarding secrets from the era when worlds were still taking shape. And whether the culprit is a planet, a process, or something we haven't dreamed up yet, one thing's certain: the solar system's edge is far stranger than we ever imagined. The Eridanus Supervoid isn't just an empty patch of space. It's a staggering cosmic desert so vast it could swallow thousands of galaxies whole. Spanning nearly 1.8 billion light-years, this cavernous region of nothingness is one of the largest structures ever discovered, a gaping hole in the universe's tapestry where matter somehow went missing. But its sheer size isn't the only mystery. This supervoid might hold the key to one of cosmology's most perplexing puzzles, the CMB Cold Spot, that enigmatic chill in the afterglow of the Big Bang. The connection between the two challenges everything we thought we knew about how the cosmos organizes itself. When astronomers first mapped the cold spot in the cosmic microwave background, they assumed it was a statistical fluke, a random dip in temperature. But as observations sharpened, a tantalizing clue emerged. The cold spot aligned eerily with the direction of the Eridanus Supervoid. The logic seemed straightforward. If light from the CMB passed through such a vast underdensity, it would lose energy climbing out of the void's gravitational well, creating a cooler patch in the sky, a phenomenon called the integrated Sachs-Wolf effect. The problem: the math didn't add up. The supervoid, though enormous, isn't nearly empty or deep enough to explain the cold spot's extreme temperature drop. It's like expecting a pebble to cause a tidal wave. The scales are wildly mismatched. This discrepancy has sparked fierce debate. Some theorists argue the supervoid might be part of a larger, even emptier structure we haven't fully mapped, a cosmic matryoshka doll of voids within voids. Others propose the cold spot could be a shadow cast by something even stranger, a collision with another universe during the chaotic infancy of our own. In this scenario, the supervoid isn't the cause but a side effect, a bruise left by a multiversal encounter. Then there's the radical possibility that we're seeing evidence of exotic physics, perhaps a flaw in the fabric of spacetime itself, a relic defect from the universe's earliest moments. The stakes couldn't be higher. If the Eridanus Supervoid and the cold spot are linked in ways we don't yet grasp, it would mean our understanding of cosmic structure and the forces that shaped it is fundamentally incomplete. Current models of the universe rely on the cosmological principle, the idea that matter is evenly distributed on large scales, but the supervoid's existence, paired with the cold spot, suggests the cosmos might be far lumpier and more asymmetrical than we ever imagined. Future telescopes like the Vera Rubin Observatory aim to probe these depths with unprecedented precision, hunting for faint galaxies or hidden matter that could solve the riddle. For now, the Eridanus Supervoid remains a paradox, a silent abyss that speaks volumes about how much we have yet to learn. Whether it's a cosmic coincidence, a sign of new physics, or a window into a multiverse, one thing is clear: the universe loves to defy expectations. And in that defiance, we find the most thrilling mysteries of all. Most galaxies spiral, swirl, or clump into chaotic ellipses, but not Hoag's object. Floating 600 million light-years away in the constellation Serpens, this cosmic bullseye defies every expectation of galactic architecture. At its core sits a dense, golden sphere of ancient stars glowing like a celestial ember. Encircling it, perfectly offset, is a pristine ring of younger, blue stars, so symmetrical it looks like someone traced it with a cosmic compass. Between them, nothing. Just a yawning gap of near-total darkness, as if the universe itself drew a boundary. This isn't just another galaxy. It's a cosmic oddity so rare, astronomers haven't found anything quite like it since its discovery in 1950. The mystery begins with its formation. Typical ring galaxies, like the cartwheel, usually form through violent collisions, one galaxy plowing through another, sending shockwaves that trigger star formation in a rippling disk. But Hoag's object shows no signs of a recent impact, no twisted debris, no distorted trails, just eerie perfection. One theory suggests a long-ago merger, so ancient its scars have faded into time. Another proposes an extreme version of galactic resonance, where gravitational instabilities in a rotating disk gradually push stars outward into a ring, leaving the core isolated. But neither fully explains the ring's razor-sharp edges or that unsettling void between core and ring. Then there's the enigma of its isolation. Most peculiar galaxies have neighbors whose gravity shapes them, but Hoag's object floats alone, a cosmic hermit. Deep field images later revealed a faint, distant ring galaxy in the background, fueling speculation that these structures might be more common than we thought, just impossibly dim. Yet even that doesn't solve the puzzle. If Hoag's object formed naturally, why don't we see more like it? The answer might lie in its timing. Its core is packed with old, red stars, while the ring brims with youthful blue ones. A clue that star formation happened in distinct epochs, perhaps fueled by a slow-motion collapse of gas clouds over billions of years. What makes Hoag's object truly mesmerizing isn't just its beauty, it's the way it forces us to confront the gaps in our knowledge. Here's a galaxy that shouldn't exist by conventional rules, a structure so flawless it feels almost engineered. Some have playfully floated the idea of alien megastructures, though there's zero evidence for such wild claims. The real wonder is subtler. Hoag's object might represent a fleeting phase in galactic evolution, a snapshot of a process so rare we've barely begun to understand it. Future telescopes like the James Webb could probe its dust lanes and stellar chemistry for answers. Until then, this cosmic ring remains a silent challenge, a reminder that even in the familiar shapes of galaxies, the universe still holds designs we've yet to decipher. The universe is supposed to expand evenly in all directions, a grand, stately inflation set in motion by the Big Bang. But something's off. Across billions of light-years, entire galaxy clusters are drifting in the same direction, as if pulled by an unseen hand from beyond the edge of everything we know. This isn't just random motion, it's a coordinated march toward something we can't see, a cosmic current so vast and inexplicable, scientists call it the dark flow. And its existence suggests that either our understanding of gravity is fundamentally flawed, or something monumental, something beyond our observable universe, is tugging at the fabric of reality itself. The discovery came in 2008 when astronomers studying the cosmic microwave background noticed something unsettling. Galaxy clusters weren't just moving apart with the expansion of space. They were also streaming toward a specific patch of sky near the constellations Centaurus and Hydra at speeds exceeding 1,000 kilometers per second. These weren't isolated cases. Over 1,000 clusters showed the same peculiar motion, defying the expectation that matter should distribute randomly on large scales. The culprit, not dark energy, not dark matter, but something entirely outside our cosmological models. One explanation is as mind-bending as it sounds: the gravitational pull of other universes. In the multiverse scenario, where our universe is one bubble in an infinite foam of others, neighboring universes might lie close enough to exert a tidal force on ours. Picture two soap bubbles barely touching. The slight deformation where they meet could create a gravitational gradient pulling matter toward the contact point. If true, the dark flow could be our first indirect evidence of a larger cosmic landscape beyond our horizon. But not all scientists are ready to jump to multiverses. Skeptics argue the dark flow might be an artifact of incomplete data or measurement errors. The cosmic microwave background, used as a reference frame for these motions, has its own anisotropies like the axis of evil that could skew results. Others propose a humbler explanation, a supermassive structure lurking just outside our observable universe, perhaps a gargantuan concentration of matter so immense its gravity reaches across the cosmic void. The problem, by definition, we can't observe anything beyond the cosmic horizon, the point where light hasn't had time to reach us in 13.8 billion years. The very idea forces us to confront the limits of our vision. What makes the dark flow so electrifying isn't just the mystery, it's what it implies about the universe's structure. If real, it challenges the cosmological principle, the bedrock assumption that the universe is homogeneous and isotropic on the largest scales. Instead, we might live in a lopsided cosmos, shaped by forces or neighbors we can't yet detect. Future missions like the European Space Agency's Euclid telescope aim to map galaxy motions with unprecedented precision, hunting for clues in the subtle warping of spacetime. Until then, the dark flow remains a tantalizing enigma, a cosmic river with no visible source, pulling us toward questions we're only beginning to ask. Whether it's evidence of a multiverse, a flaw in our theories, or something even stranger, one thing is clear: the universe doesn't just expand, it moves. And somewhere in that motion lies a secret we've yet to uncover. A star's death is supposed to be final, a cataclysmic explosion so violent it scatters its remains across the cosmos. But deep in the cosmic graveyard, some stars refuse to stay dead. These are the zombie stars, celestial phoenixes that cheat death, erupting back to life after their funeral pyres should have burned out. They're not just rare, they're rewriting the rules of how stars live, die, and occasionally rise again. Take the case of IPTF-14s, a supernova discovered in 2014 that should have faded into oblivion within months. Instead, it brightened and dimmed erratically for over 600 days, as if someone kept hitting cosmic rewind on its destruction. Normally, a supernova's light curves follow a predictable arc, a sharp peak, then a steady decline as radioactive decay powers the afterglow. But this star flared up at least 5 separate times, defying every model of stellar death. It wasn't just a dying gasp, it was a star resurrecting itself over and over, like a firework that refuses to stop exploding. The secret might lie in these stars' bizarre physics. One theory suggests zombie stars are part of a binary system, where a companion star continually feeds material to its undead partner. As the zombie siphons gas, it reaches critical mass over and over, triggering repeated mini-supernova. Another idea points to pulsational pair instability supernova, a phenomenon where massive stars, rich in oxygen and carbon, undergo violent contractions and eruptions before their final collapse. These stars don't just explode once, they convulse in a series of outbursts, shedding layers like an onion peeling itself in reverse. Then there's the most unsettling possibility. Some zombie stars might be stellar vampires, reanimating by consuming dark matter. In regions dense with this mysterious substance, hypothetical asymmetric dark matter particles could accumulate in a star's core, annihilating each other and reigniting fusion long after the star's fuel was exhausted. It's a fringe theory, but if true, it would mean these stars aren't just defying death, they're feeding on the very fabric of the unseen universe. What makes zombie stars so transformative isn't just their defiance of expectations. it's what they reveal about the messy, nonlinear nature of stellar evolution. For centuries, we've pictured stars' lives as predictable arcs: birth, stability, death. But these cosmic revenants prove that chaos lurks in the margins. They challenge us to reconsider what death even means for a star, suggesting that the universe's recycling program is far more creative and far less final than we ever imagined. Every time we spot another one, it's a reminder: in the cosmos, even endings can have sequels, and the next chapter might be stranger still. Tucked away in the constellation Monoceros, Latin for unicorn, lurks a cosmic paradox so strange it seems almost mythical. This is the unicorn, the smallest known black hole in the universe, a gravitational pebble so lightweight it defies everything we thought we knew about how these cosmic monsters form. At just 3 times the mass of our Sun, it straddles the razor's edge between impossibility and reality, challenging the very definition of what a black hole can be. The unicorn's discovery began with an unassuming red giant star, its light flickering in a way that caught astronomers' attention. Most red giants pulse rhythmically as they near the end of their lives, but this one's wobbles were erratic, as if tugged by an unseen dancer. After ruling out planets and stellar companions, the only explanation left was a tiny, invisible object with enough gravity to warp the star's motion, yet too small to be a typical black hole. At just 3 solar masses, the unicorn blurs the line between neutron stars and black holes, occupying a theoretical mass gap where astrophysicists long believed no black holes could exist. This raises a haunting question: how does something so small collapse into a black hole at all? Traditional models suggest stars must weigh at least 5 times our Sun's mass to form a black hole upon death. Anything lighter becomes a neutron star, a dense corpse where matter resists collapse, but the unicorn implies there's more to the story. Perhaps it was born in a binary system, its outer layers stripped away by a companion star before it could fully ignite. Or maybe it's a primordial black hole forged in the chaos of the Big Bang itself, lurking undetected until now. Then there's the mystery of its invisibility. Unlike supermassive black holes that scream their presence with blazing accretion disks, the unicorn is dark, its weak gravity barely disturbing the cosmic stillness. This suggests there could be countless others like it, hidden in plain sight, subtly tugging at stars we've written off as ordinary. If so, our galaxy might be teeming with these ghostly mini-monsters, each one a silent challenge to our understanding of stellar evolution. What makes the unicorn so revolutionary isn't just its size, it's the doors it opens. If black holes can form this small, they could solve puzzles ranging from dark matter's nature to the origins of gravitational waves. Some theorists even speculate that tiny black holes might be the elusive, dark matter binding galaxies together. Future telescopes, like the Vera Rubin Observatory, could hunt for more of these phantoms by tracking subtle stellar wobbles across the Milky Way. For now, the unicorn remains an enigma, a cosmic David among Goliaths, proving that even the smallest anomalies can rewrite the rules. Whether it's a fluke or the first of many, one thing's certain: the universe loves to defy categories. And in that defiance, we find the most thrilling discoveries of all. From vanishing stars and rogue black holes to ghostly radio rings and galaxies spinning backward, we've journeyed through 25 cosmic anomalies that defy logic, rewrite physics, and leave even the brightest minds humbled. Whether it's the wow signal's eerie whisper, the Great Attractor's unseen pull, or Hoag's object's perfect geometry, each mystery is a reminder that the universe thrives on the unexpected. These aren't just quirks of space, they're cracks in the foundation of what we think we know, beckoning us to peer deeper into the unknown. But here's the beautiful truth: every anomaly is a gift. They force us to question, to innovate, to admit that for all our telescopes and equations, we've barely scratched the surface of reality. Consider this: dark matter and dark energy make up 95% of the universe, yet we don't even know what they are. The cold spot might be a bruise from another universe. The dark flow could hint at realms beyond our cosmic horizon, and zombie stars, they laugh in the face of death itself. If these enigmas teach us anything, it's that curiosity isn't just a trait. It's our compass in the vast, uncharted dark. So what's next? Maybe you'll be the one to crack a cosmic code, or maybe you'll simply gaze up at the night sky with fresh wonder. Either way, the adventure doesn't end here. Hit like if this journey through the universe's strangest secrets blew your mind. Subscribe to join us as we uncover more mysteries, and drop a comment below which anomaly left you the most awestruck. Was it the diamond planet, the whispering void of Boötes, or something we didn't even mention? The cosmos is full of stories waiting to be told, and the next chapter. Well, that's up to all of us to discover. Keep looking up. End of video.